Good morning. Welcome to Krishna's classroom. What we have proved in our last lecture is a very fundamental result. It says that the fundamental theorem of integral calculus in the context of Lebesgue integration theory on a compact interval AB is valid if and only if the function is a absolutely continuous function. It's a very powerful result. So only absolutely continuous functions come under this class. And what we are trying to do today in this lecture is to consider some of the consequences. And we begin with a corollary to this main theorem. It says, even if the function is monotonically increasing, the fundamental theorem of integral calculus is valid if and only if the function is absolutely continuous. Now, this is relevant because there are monotonically increasing functions which are not absolutely continuous. So, we state the corollary and make some remarks about it later. So, let A be monotone on the closed bounded interval AB then if and only if integral f derivative now we have not made any specific mention about the existence of f derivative because it is guaranteed. The existence of f derivative is guaranteed by the fact that f is monotone on the closed bounded interval. It is almost everywhere differentiable and the derivative exists. But the problem is whether it is also integrable. Okay. This problem, that is the fundamental theorem of calculus, integral a to b f prime equal to fb minus fa is valid or not. The validity of this statement is true only when f is also absolutely continuous on the interval AB. Because this is relevant because there are monotone functions which are not necessarily absolutely continuous. So, even monotone continuous functions which are not absolutely continuous on the interval AB. That is the relevance of this. So, you give the proof. The proof is very simple. It is based on the outcome of the previous theorem. So, we assume f belongs to then of course by the previous theorem f derivative exists almost everywhere on AB, and f derivative is integrable on further so this does not require f to be monotone. So all those assumptions are not required for this part. Once it is absolutely continuous by the previous theorem, all these statements are true whether f is monotone or not. Okay, so that's about it. Now we want to prove the converse of this result. Therefore, what we have proved here is, I will put it this way. Okay. Now we prove the converse of this. Assume f is monotonically increasing. It could as well work with the decreasing one, with if you change the sign and then apply the result. So that's no difficulty. And integral a to b so this is what we assume. Now we want to prove that this is absolutely continuous. So claim so we shall develop the proof by additivity over the domains of integration. This we have seen for Lebesgue integration, this is valid. We have 0 equal to, we just write this. So this is equal to integral a to b f prime minus f a which I split up into two parts. So this can be written as integral from a to x and x to. Okay, so let us do that. We split this integral into two parts, where x is some arbitrary point lying between a and b. We can write this as integral a to x f prime minus fa plus integral a to b, a to x to b f prime minus fx. Now, okay, integral a to b is less than or equal to 0. This is one of the inequalities that we have proved. In any case, this inequality is valid. So also, because here x belongs to integral a to b f derivative minus fb minus fx a to x, this is x to b. Is less than or equal to 0. Therefore, the 0 has been now split into two terms. Each one of them is less than or equal to 0. Therefore, the only possibility is that each one of them is equal to 0. Sum of two zero implies each of them is 0. Therefore, what do we have? integral a to x f derivative equal to x minus f, or so this result is true for monotone functions provided, or if and only if the function is also absolutely continuous. Now this is relevant in the sense that, I will make a remark here. Monotonicity is not a replacement for absolute continuity. The Cantor-Lebesgue function phi is monotone continuous on 0, 1. However, it is not absolutely continuous on 0, 1, because, and one cannot say that so you see that absolute continuity is required even when you assume f is 1. Now we look at another result, which is again a consequence of it and a very useful result. So we prove the following theorem. Over the closed bounded interval AB, then f of x equal to 0 for almost AB if and only if integral course, in the previous theorem, we have assumed x is an arbitrary point on the interval. Just a reminder. So we proved this theorem. That is integral f true for on every open interval x1 to x2 implies f is equal to 0. Now, from the assumption, we first assume first one assume almost everywhere on AB. Then clearly because f is equal to 0 almost everywhere on the interval AB. Therefore, the consequence, so therefore f is identically equal to 0 almost everywhere. Okay, therefore integral x1 to x2 f equal to 0 for every x1 x2 continuity. Now we prove the converse. So what we want to prove is the reverse implicate. Suppose equal to 0 then integral over the open sets, open intervals AB for every open set open contained in contained in table. Further, we know that if E is then E is the disjoint union of the disjoint countable union of open units. That is E is equal to infinity n A n B n empty for n not equal to therefore this implies integral over E equal to because over each A n B n, this is because that is the reason. So each one of this is 0, therefore that is. Now this result holds for all G delta sets. Why it is so? This is because every G delta set is the intersection of a countable descending collection of open sets. This is because every G delta is the intersection of a countable collection of open sets. So for each open set, this result is true. Now, if you take a G delta set, it can be expressed as the intersection of a countable collection of open sets, a countable, rather writing more precisely, countable descending collection of open sets. So you have got G. If G is that set, then G is equal to intersection of En infinity, En open, and En plus 1 En. So this is the, and because of this, you see, you can easily see that this is also valid for every G delta set. So now we have come all the way from intervals to open sets and then to what are called G delta sets. Now every measurable, this is one of the theorems, every measurable subset E of is of the form E naught, where G is a G delta set and E naught is a set of so what you have is M of 0. So you take any measurable set E. See, E can be E measurable. E can be written as where G is a G delta and E naught is a set of measure 0. So we apply the previous result. Know something about what happens on a set of measure 0, integral on a set of measure 0, and also what happens on a G delta. Claim that equal to 0. Almost all E measurable sets This is because what you have is this E is equal to now you see that this is what we want to conclude that f is 0 almost everywhere. This is equal to integral over g slash e naught is e f plus integral over e naught f, and that's equal to integral over f. Why? Because integral over e naught f is equal to 0, because f is 0 everywhere on e naught. Now we have this result, integral over e what next? So this is what we have to do. Now we cannot straight away conclude that f is equal to 0 on E. Why? Because f may be positive. I mean, there may be a sort of compensation, a set on which f is positive, a set on which f is negative, and then they compensate each other. So now define E plus to be the set of all x belonging to AB to 0. Split this into two parts. So both E plus and E minus are measurables on AB. So we have integral, okay, and right, so we look at f plus and f minus. F plus is those so f plus and f minus, of course, So both these are measurable functions. Okay. Therefore, we can now write the following: integral over a to b is equal to 0, which implies equal to 0. And integral a to b which is equal to 0, which implies and therefore which implies because f so that completes the proof. And this is true for every E. That gives the power for this conclusion. Okay, so we conclude our lecture here for the day, and we take up further properties of this in our next lecture. Thank you very much.